Now that we have a good understanding of limits, we are ready to look at continuous functions. So we're first going to develop a graphical model of what it means to be a continuous function. We're going to use that model to develop a precise definition, and then we're going to think about and visualize different kinds of discontinuities that a function can have. So the question of what it means for a function to be continuous, at least our intuitive understanding from calculus, is there are no breaks in the graph, no holes in the graph, or no vertical asymptotes. So if we're talking about breaks, here's the situation we're looking at. We have the graph coming up to L1, but not quite getting there on the left, immediately jumping up to L2 on the right, and then continuing on. This is called a jump discontinuity. And what we have is a left-hand limit L1, a right-hand limit L2, but those two numbers are not the same, so the limit does not exist. So the lesson from this example is that if we want a continuous function, we need the limit to exist at the points where it's continuous. So holes are another way we can have a little break in the graph. And here's an example. This is called a removable discontinuity. And in this example, we actually do have a limit L. But the function does not exist, so there's nowhere to put a point in that hole to fill it in. So the lesson that we get from this one is that if we want to have a continuous function at x equals a, the function value at x equals a must exist. And then finally, we get another example of having a hole in the graph. Here this is again called a removable discontinuity. Again, the limit exists. In this case, since we put up that point for f of a, the f of a also exists, but they're not the same. And so the lesson here is that not only does the function value at x equals a have to exist, and the limit as well, but they must be equal. So that brings us to the definition of a continuous function. If f is a function from the interval I to the real numbers, we say that f is continuous at x equals a if the limit of f of x as x approaches a is equal to f of a. And if we want to put this into delta and epsilon terms, every time we have a number epsilon that's greater than 0, there exists some corresponding delta greater than 0, such that for all x in the interval, such that absolute value of x minus a is less than delta, we have absolute value of f of x minus f of a is less than epsilon. That looks very similar to the definition of a limit. Notice, though, that we're removing the requirement that x not be equal to a. Here, it's perfectly okay for x to be equal to a, since we're trying to show that in addition to the limit existing, we want to also show that f of x equals f of a. All right, so if we wanted then to determine whether or not f is continuous at a point x equals a, we got to do a couple things. We got to find the limit, we got to find the function at x equals a, and then we got to show that those two quantities are equal. All right, so what are the different kinds of discontinuities? We're going to give some. We've already kind of given some names to them. We'll make them more official in a little bit. So remember that continuous means that the limit as x approaches a of f of x is equal to f of a. There are three things that can happen to make this go wrong. First of all, it could be possible that the limit does not exist. It could be possible that the function value at x equals a does not exist. Or the third thing is that both of those things exist but are not equal. And that leads us to some different ways of categorizing discontinuities. We sort of talked about jump discontinuities before. The precise definition of a jump discontinuity is the limit, the left-hand limit exists, the right-hand limit exists, but are not equal. And a removable discontinuity means the limit exists, but either the function value at x equals a does not exist, or it's not equal to the limit. So I think you're pretty well equipped to work on the continuous function problems. They're very similar to the limit ones. We just have to check that the function values are the same as the limit. So you can go ahead and click on the link below this video to see the activities.